Very good afternoon to all of you. I would start with an apology for being late. I was supposed to be here in the morning, but I reached Vilnius last night at 11:30 p.m. and then I couldn't sleep until 5 a.m. in the morning. And I was supposed to drive from Vilnius to here, so I thought better sleep for 3-4 hours and then travel. So I'm sorry for the delay and thank you for your patience. I would like to especially thank Roberta's and team for the wonderful technical organization, and also Gidire and team for the wonderful local organization. Probably without her I would not have been here because we had nice, excellent communication and things were coordinated so well. And today I'm going to talk about cyber physical systems, which is I would say, upcoming research topic. But still, I would try to maintain a more generic ambience, because I saw the technical schedule and I saw that there are a lot of papers in different areas, so I would like to throw a lot of ideas in different areas, and I guess together we can learn and do something. So that is my objective. And my main focus today will be on data analysis. So I would like to especially touch various methodologies coming out from computational intelligence and some of our own research achievements in that area, some of the latest works, what we have done, and how we can various types of data, because nowadays, because of the internet and variety of sensors, embedded systems, we have to deal with a lot of different types of data variety, from numerical, categorical, to text, to complex graphs. So how can we understand some of these data so that we can manage our information systems much better? So these are my coordinates. If some of you needs more information later or some later papers, you can always email me, or you can also find from my personal webpage. So I would like to give a quick introduction to cyber physical systems for those who are not familiar with this area, and some of its nice applications. Then I will quickly focus on data analysis part, especially focusing on adaptive representations, how to analyze data so that we can get a more accurate model with less complexity, probably less computationally expensive, and in some cases it is more interpretable. So how we can go about these things all together. And all the way I will try to give you some application examples so that all of us will keep awake. I guess I am standing in between a nice lunch waiting outside and this talk. So we will try to make it very straight and simple. So for those who are totally unfamiliar with this area, basically it is our old research area which we call as embedded systems, where we have independent systems running within a big system, and we actually don't see that. But nowadays, because of the internet, we are able to connect these independent embedded systems, and we can make use of the internet or the cyber infrastructure to do things more automatically and more the way we wish. And how old is this? So basically it is a evolved area of cyber-physical systems, which means that it has been there over decades. But because of the development of the internet and the thrust of various funding agencies, this area is getting a lot of attention recently. And you can see a variety of applications, especially in automotive areas, chemical processes, civil infrastructure. For example, you want to control a valve of a dam, or you want to control a nuclear power plant by sitting in some other city or some other country, or you want to control the traffic lights in Vilnius city by operating from this city. So you can imagine a variety of interesting things. Besides entertainment, consumer appliances, it has really penetrated in different areas. So basically we can call it as a network of interacting elements with physical input and output instead of standalone devices. So which is more like a traditional embedded system. So I would like to quickly go through some interesting application areas which I took from a European project. So these are all mostly, some of them are really ideas, not even done in practice. For example, in the past, we detect a forest under fire when almost half is burned, because we don't have the system to detect in real time, to control it. So basically it is remotely seen, and then by the time we send fire force, fire engines, planes to extinguish, half the forest is burned. But now we can imagine if we have interesting monitoring systems like tuned with cyber-physical systems where we can detect in real time and then we can actually turn on extinguishers in real time so that we can control the aftermaths of forest fire. Similarly, we can use for pollution monitoring. Pollution is a big problem in big cities. So if you have right sensors and even for controlling such pollution automatically, we can actually control pollution in a very nice way. Natural disasters, we have monitoring systems for tsunamis, earthquakes. Similarly, we can also have such systems for monitoring dams, for monitoring rivers, for monitoring cliffs to prevent landslides. So you can imagine a variety of application areas. Saltwater levels where you have a mixture of river and sea. Sometimes it can affect the flora and fauna. So we need to monitor that very closely and then take appropriate measures. So whether we can do such things in real time. Smart cities, we can think about variety of applications from handling traffic congestion in real time. Because nowadays, most of the things are happening when things have happened. For example, we see a long queue of cars, the streets are crowded, cannot move. Then we try to do something. But whether we can sense the flow of traffic and then we can control the flow of traffic or even the speeds. For example, if you look at our traffic signs, basically it's all fixed, 50, 60, 70, 100. Whether we can have variable traffic signs in accordance with the traffic conditions. Waste management is often another big problem in some big cities. We can also keep track of such waste. And nowadays, you can find a variety of sensors which are very cheap. Probably 10, 15 years ago, these sensors were very expensive. Now you can buy these sensors for a few cents. So even a waste bag can afford to have a sensor. And when we have sensors, we can monitor, we can get data, and then we can do something to manage all this. Even leading to intelligent transportation systems. You can think about various applications in health, from monitoring terminally ill patients whether it is for surgery or even for monitoring sports people, continuous care. So I guess the sky is the limit in terms of applications. E-commerce is a very interesting area too. Imagine if each package has a sensor which could be monitored. We can really see how our packet is moving from point to point. Just like nowadays we can see how we move around, right? It's very easy if you carry a mobile phone. Basically anyone can see where you are right now. And imagine if you can have that with our packagings, containers, we can manage a lot of things in a very nice way, from storage to transportation, shipment. We can manage inventories in a very nice way. So basically, I would say there are a lot of opportunities. And if you look at our cyber infrastructure, I would say in internet in general, you can see the massive volume of data. Whether it is social, whether it is e-commerce, whether it is etc., you can see variety of data coming from various applications. So many number of videos, so many number of tweets, so many number of emails, so many number of Facebook views, etc. So whether we can convert some of these to get meaningful information. So that is our challenge. For academia, I guess we need to develop new infrastructures to manage these type of complex data, scalable information systems. And it is a big challenge. And especially in the data mining community or data analysis community, nowadays we talk about 4 V's. First is the massive volume, or we call as big data. Second is the velocity, especially when you have sensors or instruments or a variety of applications. You can imagine just not something which is gone, but something that is happening. And the velocity is very important, especially for e-commerce, or even for example, catching a bad guy. Because if things are gone, then it is gone. So we need decision making in real time. And also data in many forms, from numerical, categorical, which are very familiar. Nowadays we need to also understand multimedia data, whether it is pictures or videos, and even text. And in modern days, it will be also good if you can analyze graphs. Because nowadays we see everything as a network. If you look at each of us, we can relate everything to a network. We have a network of friends, we have a network of research topics, they are interlinked with something else, almost everything. It will be very interesting if we can link these networks or understand these complex networks. And it is not small, and this can be hundreds of thousands of nodes. And sometimes you also need to deal with data in doubt, or we call as veracity. Because when you have different sensors monitoring different applications, we don't know whether this data coming from this sensor is really from this application or from some other application. So we also need to deal with uncertainty. So these 4 V's, actually there are many more V's, but this is more like a summary. So handling these 4 V's is very, very complicated and involves a lot of research challenge. Especially it depends on the application area. This is again a matured area, big data. If you ask any computer science department or information system department in any university, there will be at least 1 or 2 professors whose main area now is big data. And this has been since last 10 years. And you can see a variety of nice frameworks. From basic Hadoop MapReduce, which is more like a platform for analyzing data, or more like a kitchen to cook your food. And then you have specialized software, for example, like MATLAB, SPSS, SAS, which can do analytics. And then if you want to go a little bit more deep, then many a times we need to develop our own algorithms or methodologies. Whether it is network analysis, whether it is for security, or whether it is social media analytics, we need to develop our own frameworks. For example, if you have hundreds of thousands of tweets, and then you want to make a summarization of these tweets, then really we need to have some of our own methodologies. We cannot use some standard frameworks. Probably we can use some basic layers, for example, like Hadoop, MapReduce, etc., and then we need to develop our own framework so that we can sit on top of that and then try to develop methodologies. And the challenge here is to develop algorithms, frameworks that can also work in real time. Because if you develop something, it doesn't work. Or it gives an answer after several hours, it might not have any value. So for example, if you want to develop a software for detecting human face in real time, so you can think the challenge would be to decide which all features I would use. And what storage method I would use. And what retrieval method I would use. It is more like we store things in a kitchen. For example, if you have all these spices, all these cooking things scattered around, it will be very difficult for us to find something, right? The same way, if you try to understand what all features are important, how to store this, and if you use the right retrieval method, then we would succeed in developing a very nice information system. Especially in the modern world, when you're faced with chaotic data, applications which requires performance in real time, or complex manufacturing applications which requires productivity, accuracy, reproducibility, etc., etc. So basically we can consider analyzing data using 2 methodologies. One is using very precise models, which many a times doesn't work in practice. On the opposite side is using approximate models, which is entirely relying on approximate reasoning, function approximation, and randomized search. So I would quickly introduce what I mean by these terms. Function approximation. So the idea is to build a function. You have some inputs and you want some outputs. So the idea is to build a model or a function. You can think about classical regression methods, and the modern takers are like neural networks, decision trees, support vector machines. And we have seen a lot of success in a variety of areas. And especially when the application gets tougher, that is, when you have the decision boundaries more complex, then you might find very challenging to use classical models. Then we need to somehow understand or develop new methodologies, new algorithms, so that we can redesign the decision boundaries. Many times you also use clustering for applications, because clustering helps us to group similar looking objects together and other objects as different as possible. So the challenge here is to keep inter-cluster differences as far as possible and intra-cluster difference as close as possible. This is a very nice slide which MATLAB uses for advertisement for the fuzzy logic toolbox. So precision is very good, but sometimes if you are too precise, then it doesn't make much sense because the application would fail. So many real-life problems we can solve if you use approximate reasoning. There are a variety of tools for doing that, for example, fuzzy logic, rough sets, etc., etc. And very often we also come across challenges. How to make something better. Optimization. We can see this in different fields. For example, what is optimal shape of a bottle? Can someone in this room tell us? Almost impossible, right? What shape? Or whether it should look more aesthetic, whether it should have long life, whether it should have less weight, cost versus utility, or for what purpose. So it is very difficult even for humans for us to decide what is the best. And how can we imagine a computer doing that for us? For example, you might have seen the new Boeing planes. It has something called winglets. The wings towards the end, you might have seen it as slight bends. And it was actually designed using some of the methodologies, bio-inspired algorithms. Better than this, but this is the best we could get. So now I will go a little bit more core topics, and then I will try to illustrate some of our own developments in some of these fields. I guess neural network doesn't need any introduction. 50 years old, very well established methodology used for function approximation, regression, classification, pattern recognition. But if you look at a neural network, then still we have a lot of questions and answers. what is optimal architecture for a given problem? If you have 100 inputs and 5 outputs, and you have 100,000 examples, what sort of neural network I should use? How many hidden neurons? How many layers? What activation function? What parameter values? And what learning method I should use to optimize these parameters? So basically we end up with more questions than trying to solve a particular application example. And this is exactly in line with the popular no free lunch theorem. Woolpert and McCarthy in 1998, they put forward a very nice theoretical framework with proof which says that there is no single optimization algorithm which could work well for all class of problems. For example, if I develop an algorithm and say that my algorithm is the best, you cannot beat it, that means I am stupid. Because it is not possible to have a single algorithm that can work well for all class of problems. You might have some algorithm that could work well for some data, some class of applications, but when you use the same algorithm for another class of application, then you could see a disaster. And many of our neural network researchers, if you look at papers, you are actually verifying the no free lunch theorem. At the same time, we have a wonderful mechanism for approximate reasoning. Actually, it was born in this part of the world, so it is very interesting. Professor Jan Lukasiewicz, I guess he was originally from Poland. And Professor Sade took it forward, defining more precise methodologies, especially from an application point of view. He provided a framework to model imprecision uncertainty using the concept of membership function. So instead of saying 0 and 1, we can say 0.4. We can say that he is 40% old, rather than saying he is 1 or he is 100% old. Because it depends from person to person, or even sometimes culture, nationality. So fuzzy logic provides a very nice framework to model implicit uncertainty. But again, if you have tried to develop a fuzzy expert system for solving some practical application, then there are a lot of challenges. We need to define relevant input, output variables. Because if you have too many inputs, then we have the problem of curse of dimensionality, too many rules which cannot be used for practical applications. We need to decide a relevant fuzzy inference system. For example, the simple Mamdani system, Takagusuge no Tsukamoto, or your own inference methods. If-then rules, you need to define the membership functions, the shape, the numbers, how we encode the rules, and many others. From optimization, I would focus on the class of evolutionary algorithms based on Darwin's theory of natural selection. Ideas fitter the parents are, they will find the opportunity to get food and produce offsprings. And it's believed that offsprings are always better than the parents. So we start with a population of solutions, we select the best, we try to alter them using some operators, mutation, crossover, we get the next generation of solutions, We see whether we are happy with those solutions. If not, we keep on doing this. Very simple flowchart and a lot of success stories. So the plane which I have shown you, the winglets, actually was designed using this symbol algorithm. And the modern trend is to sometimes hybridize, because for many practical applications, we don't know whether we need some functional approximation, whether we need some approximate reasoning, or whether we need some optimization. So many times we need to have a combination of these methods. Depending upon the performance so far, we need to learn and adapt. At the same time, we also need the best solution. So we need to learn from experience and also explore the search space as much as possible. And then depending upon the environment, the feedback, we can tune the model much better. Okay? So you can think about a complex information system inside. And the idea is to build a model that is probably accurate, interpretable, less complex, etc., etc. We can actually define our own requirements. So I will try to show you some application examples of some of these methods which we ourselves developed. And one is designing a fuzzy expert system. Like I mentioned earlier, if you have a large number of inputs, then we have what is called as curse of dimensionality. We have a problem with rule explosion. So the idea is to break the rule bases into smaller rule bases, something like this. For example, if you have 4 variables, x1, x2, x3, x4, so basically you can have the model like this. Sorry, my pointer is not shown there. You can have the model like A, or the model like B, C, D. Okay? And you can imagine if you have hundreds of variables or thousands of variables, how we can build this structure. Okay, so that's a challenge. And we try to use a evolutionary algorithm which could design that tree structure, and we use another evolutionary algorithm which can also fine-tune the parameters. So basically, the algorithm will somewhat automatically design the structure. At the same time, it will also design all the parameters inside, our if-then rules. You can imagine if it is Takagi Sugeno, you have the input, membership function parameters, and the rule consequent parameters. So here we have 3 inputs and you have 2 inputs. So all these parameters inside the rule basis are again optimized by an evolutionary algorithm. Basically, that's very simple. You just need to define what you call as an instruction set. So +2, +3, x1, x2, x3, x4, +2, +3 are the operators, and x1, x2, x3, x4 are the inputs. So you just give this instruction set, and the algorithm will automatically design what you call as trees. So for example, a tree like this can be transformed to our real expert system, something like this. So +3, plus 2 means it can take 2 or 3 arguments. Okay? So just to give you a flavor, what it can do in real life is, this is actually a popular data set, pattern recognition iris data set. So you can see that 10 runs, we try to run the algorithm 10 times, and the second row, the recognition rate, that is accuracy during the 10 run. And the average accuracy is 99.6. And this has 4 features, so you can see in some cases it only requires 3 features. The row 3, which shows that sometimes it requires only 3 features and still it can get 100% accuracy. And we can actually get different trees. For example, we have a tree on the top left corner, which may look small, but it may not be so accurate. But if you have a tree like this, we have many number of rules, but it is more accurate. Okay. This is another popular benchmark, the wine data. I think it has 13 features. So you can imagine if you have 13 features and if you use a simple fuzzy expert system, if you have 2 membership functions per input, then you have 2 raised to 13 rules, right? So many number of rules. And here you can see that number 4, the number of rules are reduced to 16, 12. So average is about 16 rules. And the number of features, 5, 4, like that. Okay? Again, we end up a small tree, big tree, and the user can decide whether accuracy is important or interpretation is more important. So that was like a past story. And then we try to design with a multi-objective approach. We cannot really compromise accuracy. At the same time, we also need a nice interpretation. So we try to design a tree model with a multi-objective approach. Is anyone familiar with this topic, multi-object optimization? All right, okay. So I could see just a few hands. So it's again a very interesting research area because of its wide applications. Because for many practical applications, especially from an optimization point of view, we have multiple objectives. And many times we need to make a trade-off. Accuracy, complexity, how can we build a fair model? So this research topic deals with that very interesting topic, and how to manage this is using variety of methodologies. Solutions are distributed, and how can you have that, what you call as Pareto front? So we need to have proper density, we need to have proper selection, and we need to have proper fitness assignment. And in our case, we try to use multi-objective genetic programming because we are dealing with trees. So genetic programming also deals with trees. So we start with the population of solution, and then we evaluate, and then we have an archive which actually manages the best solutions. And that archive is updated during every iteration, and we get a new archive, and we try to do this procedure, keep on doing this until we get a required solution. So we try to use that for building our trees. So this is actually the algorithm for multi-objective genetic programming. So since it is a bit technical, I will not go into details, but if any of you have any questions, we can discuss this after my talk. So basically, this is what it is. So if you have error versus complexity, and error goes from small to large and complexity goes from low to high, you can see we have simple but inaccurate models on one side, and we have complex but accurate models on the other side. So how can you have a trade-off? So that is a challenge. Okay? That is a simple issue here. So again, we try to use an algorithm, a flowchart like this. So we try to use the multi-objective genetic programming for designing the structure of the trees. And then we try to use a differential evolution algorithm, which is also an offshoot of evolutionary algorithm. And we have an outer loop for designing the structure and another loop for designing the parameters. And you keep on doing this until we get the required solution, and very simple. And here I want to emphasize, we try to implement type 2 fuzzy systems as well. I'm not really sure how many of you are familiar with type 2 fuzzy systems. Any of you familiar with type 2 fuzzy systems? Type 2. Okay. I could see again a few hands. So type 1 fuzzy system is very straightforward. For example, we say membership function is 0.5, that's it. In type 2, even this 0.5 is modeled as a fuzzy, with a fuzzy concept. Within some interval or within some dimension, we can define this type 2 fuzzy set. So it requires more computation, more parameters, but some research has shown that type 2 works better than type 1. So here we are trying to explore type 1 and type 2. So type 1 hierarchical fuzzy system, and this is for a very nice model, a control system model. Equation is like that, and we are trying to build a model. Type 1 fuzzy system, single objective. We try to do some weighted average of the objectives. Top left, type 1 single objective. Top right, type 1 multi-objective. You can see the error has gone down from 0.0043 to 0.0041. Error has decreased. And even the complexity, if you look at the complexity, this has 3 blocks, that has only 2 blocks. The number of rules has also decreased. Type 2, error is 0.0034. So you can see if you use type 2, even a single objective, you can see the error has gone down. It helps. And if you use multi-objective type 2, you can get 0.0028. Okay, so type 2 multi-objectives works better. This is for another control system. So we can see the training and test performance, and this is the number of parameters, because we model the complexity using the number of parameters. So you can see the number of parameters. Best is 20, mean is 71.6. So type 1, single, multi, single, multi. The first 2 columns are type 1, and the last 2 columns are type 2. So you can see multi-objective helps when compared to single objective. And this is the mean square error and the correlation coefficient, the best mean standard deviation. Okay, so you can clearly see that multi-objective works better, especially type 2. Here again you can see the tree structure. Single, this side is single, that side is multi-objective. And the top is type 1, the bottom is type 2. This is a very nice practical application, which was a Marie Curie European project, an industrial project where our task was to design a functional approximation model, and we had 300 features. So with 300 features, it is impossible to have an expert system, because you can imagine even a 2 membership function, you have 2 to the power of 300 rules, thousands of rules. So we try to use our type 1, type 2, and you can see that using type 2, we only require 4 features. So type 2, so we require only 4 features, and we can have a very nice approximation. And with type 1 also, we require only 7 features. Okay, so we are able to reduce the complexity. But I guess there were some models which were a little bit more accurate. I guess there were some decision trees which worked better than the expert system. We can also use similar methods for designing neural networks. So far I talked about fuzzy expert systems. We can also use very similar ideas for neural networks. So instead of predefining number of neurons, number of layers, we just need to fix what you call as instruction set, and then the tree will automatically build the required model. And I am not going into details since I already mentioned this for fuzzy systems. Basically the same. And this is actually a very simple flexible neural tree, what you call as flexible neural tree. And this is for the very famous gas furnace time series. It has 2 input, 1 output. Idea is to build a very nice model so that it can approximate better than any other models. So from classical ARMA models, statistical ARMA models, to all popular methods developed by many others. This is a flexible neural tree, case 1 and case 2. So case 1 is the original 2 inputs. And case 2 is the one we use some time lags. So we injected 12 time lags to each inputs, so which means that we have 12 plus 12 plus 12 plus 2. That means 26 features. And out of that, it selected 7 features, and the accuracy was considerably increased. This is again the flexible neural tree for the Mackey-Glass time series. Again, a very popular benchmark dataset. You can see very similar performance. Some practical applications, similar performance. If you use flexible trees, it seems to work better. But again, here we try to look at whether we can somehow have that trade-off, or how to manage the trade-off between accuracy, size, and diversity. So we try to have a diverse number of activation functions, which will also build diverse neural networks. And then we also try to combine these diverse neural networks, what you call as an ensemble model. So since it is very similar to the one I mentioned earlier, the fuzzy system, so I'm just straight away illustrating some results. So these are actually some results for classification. So 5 popular benchmarks: training, testing, size, features. And on the right side, you see the mean of 30 runs. So you can see that the number of features were reduced considerably. Okay, and also the accuracy as well. It is very, and compared to a traditional neural network, it is also a little bit interpretable. You can actually see how you get the results. This is for the WDB dataset. These are the connections and activation functions. This is again the previous results, a bit expanded, using 3 batches, 3 times. And this is for the regression. We also used the same example for regression. So we can see that these 5 datasets, how it works, and also some comparisons with some popular computation intelligence methods, from classical neural networks to neuro-fuzzy systems, fuzzy expert systems, etc., etc. Okay. This again shows the number of features. We can also use a very similar idea for multiple outputs. So far, I illustrated only for single outputs. We can also use it for multiple outputs, which we haven't done yet, but it is still open. We can also build complex models. For example, you see on the right side, top corner is a radial basis function network, a simple, straightforward network. It works well for small amount of data, but when you have so many samples, so many inputs, it's very difficult to get good approximation. So the idea is to build what you call as hierarchical networks like this, using the same concept of instruction sets. So basically we need to define like this, and basically inside you can have anything. It can be a fuzzy system, it can be a neural network, or can be any approximation model that could link your input with the corresponding output. And we just tried for an example, this is a very popular benchmark, the breast cancer detection. It has 30 plus features, and I guess it only required 12 features. And accuracy is better than the straightforward neural networks, trees, etc., etc. I guess I'm almost there, but do I have time? 5 more minutes? Sorry? Yeah, okay, yeah. So this will be the last application example where I'm trying to illustrate how to understand graphs. So far we are talking about numerical, categorical data, which I guess we have so many methodologies, which is sort of well known, and I guess some of you have your own methodologies. But recently, social networks has become a very important research topic, especially with the invention of Internet of Things, cyber-physical systems, sensors. All these things we can link to networks. And apparently this has been there since a long time, social networks. If you look at a very nice review by Newman, it was published in 2003. It's a very nice start. You can find very nice literature from graph theory, linking social networks, how we can model various relationships, thick lines, lines with directions, weak relations, okay, etc., etc. And graph theory also provides very nice frameworks to understand the importance, what is called as centrality measures. For example, if you have a small network like this, you need to understand who is the most important node in this network, or how can I break this network? Is there a way I can break this network? For example, if you are from law enforcement, and if you have a network of bad guys, how can you decide which node I should target so that this network goes off in a very nice way? So centrality measures provides us some interesting lead, but when you have a network like this, hundreds of thousands of nodes, and how can I say that this node is important or this node is important? And this is just a view from one angle. So you can imagine a multidimensional complex graph. So the idea is to use some technical frameworks so that we try to minimize complexity, and then we try to analyze such graphs so that we can visualize and analyze. So we started with very simple methodology, which is the formal concept analysis. This is again a very well-known, more mathematical model. Has been there since the 80s, and it seems to work very well. So basically, we try to model our social network into what is called as a table, where rows are objects, columns are attributes, and the table entry is Boolean. And for example, if you have a network like this where we have your different birds, animals, and their features. So we can pick any object. For example, if you pick duck, and then we try to derive the attributes, what features the duck has, and then we try to pick similar objects. For example, duck and goose, these have similar features. And like that, we try to add more and more, and then we try to what is called as, we call as a concept lattice. So the entire network is mapped to a table and then summarized in the form of a concept lattice. We try to do this first for the Enron data, which is a very popular email list. I guess some of you might be familiar with the Enron scandal in the mid-90s. So the government made public the email exchanges between 150 top managers. And MIT, they spend a lot of efforts to do a lot of cleaning up pre-processing to make this data more usable for research ideas. And it is actually available from MIT, if some of you are interested. So this is actually a part of the network. And if you use formal concept analysis, you get a very simple graph, which you can easily understand. The one I showed before and the one you have here. It summarizes the key factors, and then basically you can zoom into whichever node you're interested in, and then you can find more details. But this is more static data. So you have the email corpus, and we are trying to analyze using some graphical methods. I just want to illustrate another data which is time evolved. In real life, we are facing usually time evolved data that evolves over time. And for simplicity, I'm trying to use the very popular DBLP data. I guess all of you are very familiar with DBLP, right? Exploring, or I would say, really, the data is really growing at a very large scale. It is very difficult to understand nowadays DBLP, what is going on. The number of theses, articles, books, and the massive research size. I guess it's difficult for a new student to start a research topic nowadays because the world is very big. On a single topic, there are several hundreds of people working around the world. So how can you find some meaningful information from this time-evolved data? And there are also some key statistics provided by DBLP. If you look at DBLP, it shows that these authors have this many publications indexed in DBLP. And if you look at the number one DBLP, Vincent Poor is the Dean of Engineering in Princeton. He has 1,286 publications and 500 plus co-authors. I guess this slide was made probably a few months before. I think now it is much more, probably 1,400. I'm not very sure. And if you look at his academic network, his co-authors, how they are connected. Okay? And it is evolving over time. For example, if Professor Poor has written a paper today, with some other author, you can see a new line will come, right? So it is an evolving network. So how can you find meaningful information from such evolving network? So we try to use a very simple heuristic, which is based on forgetting curve. For example, we humans, we try to remember things which we think is very important. And we also forget what is not important. I know Vilnius more than the city because I had been to Vilnius a few times. And probably if I come to the city next year, I would know much better. So the more times you do things, you tend to remember. And not at once. For example, if someone co-authors a paper with someone, for example, 10 papers in 1 year, and after that there is no cooperation or no scientific productivity, or if someone cooperates with someone and produces 1 paper per year, which you think is the best in terms of scientific cooperation, scientific productivity? The second one, of course. The first one is more like some error. So this is exactly what this nice old theorem says. And we try to put it in practice. If somebody has a computer, you can go to this website, forqua.net, and you can put your own name and you can actually analyze DBLP in real time, what DBLP says about your academic network. And we try to use Vincent Poor's network, and you can actually tune some parameters and you can actually see, visualize. And if you go one step down, this is actually Professor Poor's main academic network. Some of them are his long-term collaborators, and many of them are sort of short-term collaborators, some students, some research associates, postdoctoral fellows, or some scientific friends, etc., etc. Philip Yu, who is very famous in data mining, University of Chicago. So using the software, you can actually see his network. This is actually the actual network. It's impossible to see anything. But if you go a few steps down, actually, if you have internet connectivity, you can see, you can actually tune this and the depth. So the more deep you go, you can actually see who are his main collaborators, who are his main scientific producers, etc., etc. So these are his main scientific friends during the last 40 years. We can also see the topics. We can also see the topics which Professor Yu worked during the last 40 years, evolved over time. So basically we are taking the titles from DBLP and then we are trying to map this in the form of graphs. I guess I am really running short of time, so it's time to conclude. So basically what I want to tell is multi-objective design enhances the design process for different information systems. And especially from a sensor network, Internet of Things, cyber-physical systems, I guess one main challenge is to develop algorithms for understanding topological abstractions, which I think is a very, very complex challenge. And then to transform these data flows into information flows, that is another big challenge. And many times from the academic community, I have seen that we believe in one tool and it's more like hammer and nail. So we need to have a more generic approach and then try to explore various tools and see what works best. And then managing computational complexity, that is again a big challenge. Because nowadays we have fast computers, people are actually misusing high-performance computing by not having very nice algorithms, very nice data structures, which is, I think, a very bad perspective, especially if you're from computer science or from information technology. So we need to develop nice algorithms, use the best data structures so that we can make use of the computer better. I think that's about it. Thank you so much for listening, and any questions?
Please, can you elaborate how are you using formal concept analysis to reduce the dimensionality of complex network? How do you map different concepts to the network measures to extract sub-network out from it? You can use this one.
So basically we need to convert our social network or any network into a table with Boolean entries, just like I have seen. So, and then we use this traditional FCAs to reduce the complexity. So it is very straightforward. Yeah, basically we can actually zoom the lattice. So we have a bigger lattice, smaller lattice. So if you look at the Enron corpus, we have a small lattice and then big lattice, and of course a master one. So we can have intermediate sizes depending upon how much information we want. Yeah. I guess all of them are very hungry, including me.
I would like to thank you very much for your presentation, for your visit, coming to this conference. Just a certificate of participation.
Thank you so much.
Thank you very much.
Thank you.